Okay, hello everyone. Good morning, good afternoon, and good evening, based on your location around the world. Greetings from All India Oracle User Group. We hope you and family is safe in current location. I would like to welcome you all in our AIOG webinar, which happens every Wednesday. Today we have a session on database in memory, tips and trick by Andy Rivens. During the session, if you have any question, please ask your question in Q&A panel, and we will take those questions in Q&A section. Currently, we are using two channels for this webcast, Zoom and YouTube Live, and presentation will be shared with registered participants only. You can view the presentation after filling speaker survey. Watch out your mailbox for survey link after the session. At the end of the session, we will run a quiz. Please participate and winner will get a prize. Hi, Andy. Thanks a lot for being here and taking out time for this session. Please unmute yourself and start the session.
Okay, great. Thank you very much. Let's do it this way. So hello, everybody. My name is Andy Rivens. I'm a product manager with Database in Memory. I actually work out of Oracle headquarters, so it's morning for me. I think it's evening for a lot of you folks, and thanks for joining. Actually, my email address, Twitter handle are right there. So if you have questions afterwards, feel free to ask. I'm here to help you guys understand how database in memory works. Also, I'd like to point out our blog, which I kind of consider our portal into all things database in memory, and I'll have a picture of our resources page at the end of presentation as well, where you can get more information about database in memory. But we do post technical articles and information about database in memory on the blog, so I think it's a good place to get started. With that, today I'd like to talk about tips and tricks for getting started with database in memory. It won't be so much of how database in memory works in all of the use cases. We'll chat a little bit about that, but what I really wanted to kind of give a primer on, how do you get started with it? How do you make use of it? And so with that, let's go ahead and get started. Our safe harbor statement. And so I'll start off a little just briefly about what is database in memory. It's really all about analytics, and we talk about real-time analytics, which I'll elaborate on a bit, but we called it database in memory. We could have easily called it the columnar database option, or maybe the analytics database option, because it's really focused on analytic reporting. People hear in memory and they think that everything's going to be sped up by database in memory, and that's actually not the case. And hopefully that'll be one of the takeaways you have today, is to actually learn what database in memory does, in addition to how to make use of it. We do accelerate mixed workload in the sense that database in memory doesn't use indexes, and so very often applications will have analytic reporting indexes to speed up their analytics, and those indexes can be dropped. Not all of your indexes, but analytic reporting indexes, and we'll talk a bit about that. In addition to that, since it's fully integrated into Oracle database, we take advantage of all of the existing Oracle database features, things like RAC, Active Data Guard, all of the security features of Oracle database. And it's actually very simple to implement. Unlike some products or features, database in memory doesn't require you to change any application SQL. You can use as much or as little memory as you want. You don't have to put the entire database in memory. We'll talk a little bit about the fact that you can pick and choose objects to populate in what we call the column store. And so it makes it very simple to implement as well. And it means you don't have to change your applications. So if it's certified for Oracle database, you can run with database in memory with your application. And so that's kind of our starting point. A little bit further about the analytics. So row-based databases, Oracle database has traditionally been a row-based database, very fast for transaction processing. Oracle's made its bread and butter on transaction processing. Analytics work great, but there's a lot of work that has to go on to search through all of the rows to do reporting. Very often indexing needs to be taken into account to make those kind of analytic reporting queries run faster. On the other hand, columnar formatted data or databases have been around for quite a long time. Great at analyzing and running analytics because the data vectorizes well. You can look at just the columns you need. Columnar data typically compresses well, and but it's not as good. Whoops, sorry about that. Oh, great. Columnar, I'm still columnar formatted data. Sorry about that little hiccup there on the navigation. Doesn't tend to run transactions very well because being in columnar format, the nature of the data, you have to basically stitch the column attributes back together into some kind of a row format or a so that it relates to the data involved in order to do transactions on it. So columnar formatted databases typically don't do transactions very well. Hence, you have a trade-off. And with database and memory, you get the best of both worlds. So the Oracle database stays exactly the way it always has been. Row formatted data, all changes occur in the row format. Then you can pick and choose the objects you want to populate in columnar format. It's the same object. An object always exists in the row store. It's always persistent. The Oracle transaction architecture hasn't changed. But in addition to that, we allocate memory and allow you to format or populate, if you will, objects in columnar format in addition to being in the row format. And then the cost-based optimizer can determine at parse time, do I access that data in the buffer cache, or do I access that data in the columnar format in the column store? We always keep that data simultaneously active and transactionally consistent. So you always, like I said, we preserve the Oracle transaction architecture. So you always get a read consistent view of your data. I'll talk a little bit about how we accomplish that. And anywhere Oracle database runs, database and memory can run. So it's really a very useful, I think it's a great feature, allows phenomenal speed up in analytic reporting. And in addition to that, we maintain all of the rest of Oracle database as well. So with that, very simple to implement, as I mentioned. We have one parameter, and we'll talk a little bit about how that works, that you allocate this, what we call the column store, or the area in memory in the SGA, where we're going to populate objects in this columnar format. You alter the table, partition, subpartition, or materialized view. Those are the objects that we can populate in the column store. Literally just one alter table statement and specify in memory. And that's basically it. Asynchronously in the background, we'll populate that data into the column store. It doesn't affect the actual running of the Oracle database. And then later you can drop analytic reporting indexes to free up capacity workload for further processing, either OLTP processing or maybe using that to justify using database and memory to run analytics in what we call real time or right on the source data. And so that's a pretty exciting aspect of database and memory. We have several customer stories out on oracle.com that talk about large customers that have been able to justify using database and memory because of that speed up in or reduction in workload, because they don't have to maintain all of these analytic reporting indexes they had to create in order to support their analytic reporting. So where is database and memory available? So we introduced database and memory as part of database version, well, 12C release 1, 12.102, the first patch set for 12.1. It is an option to Enterprise Edition. So you do have to pay for it if you're on premises. That's what an option is in Oracle speak. But it is available both in the cloud, on premises, both virtual machine extreme performance edition, and any of the services or Exa Cloud services. In addition to that, on ADW, it exists in Flash. So we'll talk a little bit about the fact that database and memory is not only supported in DRAM in the SGA, but we've also extended that into Flash on Exadata systems. Available on premises, of course, and then it's even available in Oracle Database XE. It's actually free in Oracle Database XE. You can use it as part of that environment. Of course, you're limited in memory based on the XE offering, but you can do it there. And you can experiment with it on things like the Developer Days VirtualBox download, which is obviously a development environment, but it is available for you to take a look at and experiment with. I use it quite a bit in my hands-on lab environments. And one other thing, database and memory is not enabled by default. The key is you do have to specify that in-memory underscore size parameter to enable it, and so you won't accidentally use it. It's you have to consciously allocate memory to make use of it. The only other thing I threw in this slide, since we are talking about, we're talking about implementing database and memory, how you would do that. And I wanted to stress that although we introduced database and memory with 12.1, realistically at this point, 19C should really be your target. 19C is where we've added quite a bit of new features to Oracle, to database and memory. It's an actively developed product. And so we added a bunch of changes in 12.2 and 18C and 19C, but 19C gives you the advantage of being current and being the long-term support version. And so if you're thinking of upgrading into either 12 or 12.2, 18C, 19C really should be you should be thinking that's where your target is. So I wanted to make sure that I got that point across as one of a tip or best practice. You might as well get started with 19C if you're getting started with database and memory. Obviously that depends on your applications and your ability to upgrade, but if you're going to upgrade, there's no point in doing it twice. So that's kind of one of the takeaways, and that's an Oracle database thing as well as database and memory. So how do I install and configure database and memory? It's very simple. It's just part of installing Oracle database. There's nothing separate to install. As I mentioned at the beginning, database and memory is fully integrated with Oracle database. So there isn't a separate piece of software you have to install. When you install 12.102 or higher of Oracle database, you're installing database and memory as well. And then the only thing you have to do is specify the in-memory underscore size parameter. But part of just installing Oracle database is installing database and memory. So it's very simple to get started. In addition to that, especially with 12.102, since 12, and that's actually, boy, I'm gonna say, that came out in like 2014, so it's actually quite old now. It's surprising. But with 12.102, we had something we called database proactive bundle patches. So if you are in an older release like that, we strongly recommend that you switch over to database proactive bundle patches, because PSUs or CPUs, and again, this is getting kind of old, but since it seems so long ago now that we're on the release updates, or RUs, that we only deliver fixes and changes for database and memory through either the database proactive bundle patches or release updates. And so it's important to stay current with either of those methods, and I included the MOS notes for those, excuse me, for your benefit, and the slides will be available to you at the end. And so you can use that as your guide, so that not only would you install Oracle database, but obviously the most recent either proactive bundle patch or release update to get all of the fixes to database and memory, and obviously Oracle database as well. But since we're talking about database and memory, that's what we care about here. In addition to that, configuring the column store, in memory underscore size, the minimum available is 100 megabytes. So you have to specify at least 100 megabytes. The sizing guide, and we have a MOS note associated with this, is that we want you to add additional memory to your Oracle database to accommodate the column store. If you steal memory from existing areas of Oracle database, the buffer cache, or maybe the shared pool out of the SGA, then your existing workload is likely to suffer. So our recommendation is to add additional memory. That may mean adding additional memory to your database server if you don't have additional memory available, but that's the in-memory part of database in memory. In addition, I have the PGA target here. Since we are going to be looking at lots of data, the database in memory is really focused on analytic reporting, which means looking through lots of data. You should take into account PGA memory requirements. And the maximum for a single process is 2 gigabytes. So I usually tell folks take the maximum number of parallel server processes you might be running if you're going to use parallel query, and multiply that by 2 gigabytes to make sure you have enough PGA memory to accommodate queries that might require a considerable amount of sorting based on large result sets or any other PGA memory requirements for the queries. In addition to that, on rack, we also recommend adding an additional 10% based on the in-memory size for shared pool data or memory, because we do keep track in rack of some of the, the column store IMCUs across the rack cluster within the shared pool. So we need about a 10% additional amount of the in-memory size or the column store size on rack. And all of this is documented in this Moss note I've put up here for your benefits. And then if you do get stuck or have trouble with sorting or PGA spilling, there is a parameter you can set to increase that to make that a little bit more efficient. But the bottom line is, which you really don't want to, you want to do as much of the work as you can during the query. You don't want to really be returning millions of rows from an in-memory query. We're really talking about aggregating data so that we can get just the result that we need back rather than having to plow through millions or billions of rows. So really the takeaway is that PGA shouldn't be a huge issue simply because we really want to leverage aggregation as part of our analytic queries to run against database in memory and do as much work as possible in the column store itself. And I'll talk a little bit about that and how you can tell and how that works. So how does database in memory itself work? I've talked a little bit about this column store, populating data. So let's go through some of the nuts and bolts there before we move on. So database in memory, one of the big things to think of is that the column store is not a cache, it's a store. So unlike the buffer cache, which typically Oracle customers can run fairly small buffer cache. It caches just the active database blocks for the data being queried. It's relatively efficient. So Oracle customers tend to not have to have large memory footprints because the buffer cache is so efficient. With database in memory, we're actually allocating that in-memory underscore size parameter. We're allocating area within the SGA in this in-memory area, this red section here. And so we're going to take up typically, and I purposely made this very large, which is within the SGA to show that we're typically going to have you create a fairly large memory area within the SGA, and you don't want to steal that memory from other areas. You want to add additional memory because we're going to populate objects in their entirety in the column store. Now, you might say, well, am I going to need twice as much memory as for the database to store everything in this column store you're talking about? And no, one, you get to pick and choose the objects. So typically you'll populate the most popular objects for analytic reporting. You won't necessarily have to populate the entire database. You get to pick and choose. Of course, you could if you wanted to, but typically our customers will populate just the most active objects that are being queried with analytic queries into the column store. In addition to that, we compress. So we'll get anywhere from a 2x to a 20x compression rate. So you won't need to have as much memory as your database size. This is very flexible in the sense you get to kind of pick and choose and decide how much memory you need. And I'll talk a little bit about how you come up with those numbers. The other takeaway here is that obviously the SGA itself has to be large enough to accommodate this new in-memory area that you're going to allocate. So the SGA target, maybe the memory target, depending on how you've and this is an Oracle database thing, depending on how you've specified your memory allocations, whether you're using automatic memory management or automatic shared memory management or defining pools individually, you need to be able to, this is the DBA part of this, you need to be able to allocate that in-memory area within the total framework of the SGA itself. So hopefully that's clear. Within that in-memory area, and this is, we'll dive just a little bit into the nuts and bolts of how database and memory works. There's actually two areas within the in-memory area that are allocated when you set that in-memory underscore size parameter. One of the areas, we call it the 1 meg pool, where we're allocating IMCUs or in-memory compression units. That's the actual columnar formatted data for the objects that you've enabled for database and memory. And then we have another area that's part of the what we call the 64K pool. I'll show you that in a minute, where we allocate snapshot metadata units or metadata about the IMCUs or the columnar formatted data. You don't really have to remember all of that other than just to recognize that that's how the architecture is built. And then my picture here is to try to explain this in a little bit bigger, bigger scenario or a bigger picture, in the sense that when you populate an object, that object will be made up of one or more of these IMCUs, which are allocated from the 1 megabyte pool in the in-memory area. And so, excuse me, an IMCU will be made up of one or more 1 megabyte extents within the in-memory area. And that's very similar to what we do with tables and table spaces and extents in the data files in the table space. In addition to that, each IMCU will have one or more SMUs associated with it. And those are about metadata, and I'll talk a little bit about what we use that for. And each of those SMUs are made up of one or more 64K pool or 64K meg extents, or 64K extents, sorry, not megs. Anyways, so hopefully that gives you kind of this picture between, I want to go backwards here, between allocating the in-memory area and how we allocate that, the pools we're using. And then once you populate or enable an object to be populated, how it actually gets physically populated into that in-memory area. Then you can see this in the $V views, because it wouldn't be Oracle if we didn't have $V views. So we have a $V in-memory area view, and notice those two pools I mentioned, the 1 meg pool and the 64K pool. So you can see how much overall memory within the in-memory area has been used, the big picture, if you will. By the way, you can't change the allocations for those two pools. The only change you can make is specifying the in-memory underscore size parameter. Then we automatically allocate memory based on that size out of the 1 meg pool and the 64K pool. And then when you populate segments into the column store, we have another view, $IM segments, which then will detail each of the individual objects as they're populated in the column store, how large they are, and one of the key fields there, bytes not populated. And there are many more attributes associated with the $IM segments view than I've shown here, but these are the key ones to show that we've fully populated the objects we've chosen in the column store. So you see bytes not populated being 0. And so that kind of tells you that we've fully populated those objects. The in-memory size there tells you how large that object or how much space that object's taking up within the column store, which then if you add the total up, it relates back to the 1 meg pool in the $V in-memory area. So as you can see, it all kind of fits together. And that's how you can tell what's populated and how much memory it's taking. This is also available in Enterprise Manager and Cloud Control. There's an in-memory central page that presents all of this in a nice graphical format, so you can do this either way. Again, it wouldn't be Oracle if we didn't offer you a lot of choices. But down at the database level, these are basically exposed through $V views. And with that, I wanted to just point out that there are other views as well. I've kind of given a summary of what I think are the most important views. Again, you'll have these slides. I don't expect you to remember all these things, but we have $V in-memory area, $IM segments for the individual objects. We have information about each of the segments, so you can see how many IMCUs are made up of each of the objects, $IM header, $IM SMU head, so it tells you about metadata units, snapshot metadata units, the SMUs. We have for in-memory expressions, IMEUs, and then join groups. And I think those are pretty much the major views that you might take a look at, but realistically, really the first two are in most cases the only things you need to really pay attention to. I'll look real quick if I can do this. Yes, just making sure I'm not missing anything for the questions. More tips to remember. The big takeaway, and folks kind of forget, not only is it columnar formatted data for analytics, but the column store is not a cache, it is a store. So when we, I'm gonna, forgive me for going back again, but I'm gonna go back to that picture here. If you notice at the bottom here, each of those objects are fully populated into the column store. And that's the in-memory part, because we're going to be able, we want to be able to scan the data, the column data associated with those objects for our queries in their entirety. So we want to be able to go through that data very, very fast. That's the in-memory part. So we recognize that the column store isn't a cache. Those objects will be populated. Once they're enabled, they'll be populated and they'll stay there in the column store for the duration of the instance or until you do an alter table no in memory. So that's a key point I want to get across to make sure you understand that it's not a cache, it is a store. In addition to that, only objects that have been enabled for in-memory can be populated. We do have other, which I'm not going to go into much detail on, other abilities. You can change the default compression level, so you can go to higher levels of compression. I kind of mentioned you get a 2 to 20x compression rate on objects typically, so you won't need as much memory as the object takes on disk, but we do give you the ability to change that. I've got several blog posts to talk about that. Priority is all about populating, initially populating. By default, the priority is none, which says you have to first, when you first access that data, but you can alter the priority so that objects are automatically populated when the database starts up. And then we talked about $IM segments, and you can actually monitor that if I do this in my hands-on lab, my example sessions, where you can actually query $IM segments and monitor the progress of population. You'll see the bytes not populated figure progressively getting lower until it gets down to 0. So with that, hopefully we're not going to run out of time here. I want to answer the question. Typically now, people will ask, well, how much memory do you need to allocate to the column store to populate my objects? And so the answer is it depends on your workload and your database, but we give you a utility, something called the in-memory advisor. We actually have Ask Tom office hours sessions, which I'll give you the link in our resources page on the blog that we just did recently, a session on the in-memory advisor. So you can go check that out if you're interested. But one of the cool things about the in-memory advisor is it uses AWR and ASH data. And note, I put this note down below that the database tuning pack license is required, because we're accessing AWR and ASH data. Again, that's an Oracle database thing. But if you have a database 11.203 or newer, and you want to see, would database in memory make sense? Is there workload going on in my applications that would take advantage of database in memory? Using the in-memory advisor, using the in-memory advisor is a great first cut at taking a look. You know, you don't have to have database in memory enabled. You don't have to install 12.102 or higher. You can literally download off of OTN or Oracle.com the in-memory advisor. It actually takes you to a MOS note where you can download the software, and there are several PDFs or white papers that describe all the details of not only installing it, but interpreting the output The bottom line is you can actually take a look at your processing in your environment and say, hey, would database and memory make sense? And so that's pretty cool. It will even go to the level of talking about how much memory you might need, what objects to populate or what it thinks would take advantage of database and memory, and what SQL statements would show the most benefit. So a very good tool to kind of determine, how much memory would I need and what objects would I populate? In addition to that, once you have that view of the objects you might want to populate, you can use the compression advisor to tell you very closely how much space in the column store those objects will take. And it supports, notice my red box here, it supports the different levels of compression that database and memory supports, which are, I'll just off the top of my head, the default, which is memcompress for query low. We also support query high, capacity low, capacity high, and you can turn it off. We have a DML, a very a low level or very light amount of compression for active objects. But the bottom line is there's several different options to compression, so you can vary the amount of compression based on your needs. We also I did a blog post on that as well, and an Ask Tom office hour session. We've done this. There's a common theme here. We actually have quite a bit of information about these different features of database and memory and how they work and how you might make use of them. And so you can go take a look at that, because one of the things that especially the DBAs will be worried that compression will add too much to the overhead. And the reality is in most cases, you can go to higher levels of compression and not affect performance by very much, if at all. So anyways, we'll move on. And then the tip is that you don't want to fill the column store completely up, because it's possible that your data will grow because you'll be adding new rows to that data, or new column values, rows which translate into columns or IMCUs that'll get added to your object in the column store. Or perhaps you'll be doing updates and the rows will be growing in width. And so then we'll populate that data or those changed columns into the column store as well. And so the column store itself is typically not static. The contents are not static. They're changing because your application is changing data. So you do need to accommodate that. Now you can see from the $V in-memory area view I showed you how much total space you're using, and you could obviously monitor that over time to see if that's starting to grow and that you might have to increase the size of the column store. But if you run out of space in the column store, what happens? And your application will still run. What happens is we'll allocate or access all of the data that's populated in the column store, and any data that's not will get from the row store. So your application won't fail. Your application SQL won't get error messages. It'll run, but it won't run as fast as if the data is fully populated in the column store. So this is just one of those things that as a management type activity, as you populate objects and determine the best objects for your application to populate in the column store, you need to take into account their growth characteristics as well. Hopefully that's clear. So what if you don't have enough memory? Again, you won't get errors, but there are options or things you can do to conserve memory, because memory's less expensive than it was at one time, but it's still not cheap. Typically, Oracle customers don't have terabytes of memory sitting around in their database servers. And so how do you maximize your memory footprint that you do have to allocate to the column store? So I mentioned compression. There are multiple levels, and again, 2 to 20x, and you can specify for individual columns different levels of compression, or you can actually exclude columns from the column store. So if you do choose to exclude columns from the column store, say columns that you're never doing analytic queries on, or maybe you have lobs, or you have columns that actually are fairly large that are only queried once in a great while but aren't part of analytic queries, you can exclude those columns. What happens if you access those columns? We'll access that data from the row store. So the query will still run, but if you've excluded columns and then specified in queries those columns that you've excluded, we'll just go to the row store to get those values. So the queries will still run. You just won't be able to take advantage of database and memory for those queries that access columns that you've excluded. But it's a way to, again, conserve memory. So we've got different compression levels here. And then you can also exclude columns from population. In addition to that, on Exadata platforms, so folks that are running Exadata, you can make use of Flash with database and memory columnar formats. So that gives you now 2 tiers of storage, if you will: memory storage, which we've been talking about, DRAM in the SGA, and then on Flash. And once you've enabled database and memory on an Exadata database, we automatically can use Flash to populate objects that have been smart scanned into database and memory columnar format on Flash, and we'll do that for any objects that aren't already populated in the column store. So that gives you now a much larger columnar footprint to manage your analytic processing on your applications if you're, again, running Exadata. In addition to that, we support Active Data Guard for database and memory as well. So if you're doing reporting on your standby database, you can actually populate objects within the column store on the standby to do your reporting if you're already doing reporting on the standby, or maybe you're going to switch over to that. That is also only available on Exadata or cloud, but that gives you another ability to, again, extend your columnar footprint. So the next question, so we usually, the technical folks will say, well, compression, and then, well, how do you handle data changes? So let's briefly talk a bit about that. So all changes, DML, inserts, updates, and deletes always occur in the row store. I said earlier, the Oracle transaction architecture hasn't changed. So all changes are always made in the row store. Actually, the column store is really read-only. Well, we don't change the data per se in the column store, and we don't change it as part of a transaction. We do, however, keep track of what's changed, what values changed, and that's what that SMU or metadata, one of the big reasons for having that metadata is so that we can keep track of changes to rows or column values within rows. And so if you do an insert, update, or delete to the row store, we'll mark those changes in the metadata. And I should preface this with the fact that, remember, the column store, there's no persistence in the in-memory area. So all persistence is managed in the row store. So undo and redo occur when changes are made to the row store, but not to the column store. So if the instance goes down, the column store, that's the in-memory part, the column store data goes away. And when the instance restarts, we have to repopulate that data back into the in-memory area. So changing the metadata, SMU in the metadata units, when you make changes to the row store, the changes reflected in metadata in the in-memory area are very efficient, very fast. It's much less overhead than maintaining indexes, because indexes are persistent. We have to generate, undo, and redo for them. So this is how we keep track of what changes occur during DML operations. So that's the first part of the story. So now what happens is, if data has changed, when we scan the data in the column store, because if the optimizer has parsed your query and decided that it's going to access data in the column store, we're going to scan that column store and we're going to see, oh, well, wait a minute, there's values have been changed. We need to go get to the row store to get the most current value for those columns that have changed. And so what we'll do is we'll read the IMCU, we'll pick up the changes in the metadata, and any changed column values we'll go get from the row store. Typically, those will be in the buffer cache because they'll be fairly new changes, and I'll tell you why in a second. But what we'll do is we'll always give you a read consistent view of the data. So we'll never violate Oracle's transaction architecture. We'll always give you a read consistent view of the data, no matter what has happened, whether it's changed in the row store or not, whether it's we've just marked it as changed in the column store. That's the good news. And then in the background, not only will we initially populate the object, but as data changes within each of these IMCUs, once we hit a threshold of changes, we'll then in the background repopulate individual IMCUs in the order to repopulate the changed data back into the IMCU, and then we'll switch over to it. So ideally, all of the IMCUs that make up an object in the column store will never have changes because we're always going back and repopulating in the background. There are some parameters to control that. The defaults typically work well for everybody. And this is actually a pretty efficient process. As you can see, we actually keep both available during the repopulation so that we're as efficient as possible for scans that occur even while we're doing what we call repopulation. And in addition to that, we did a YouTube demo with the Real World Performance team that shows that OLTP workload, as long as there's CPU headroom for your analytic reporting, if you're doing what we call real-time analytics, or if you're actually running analytics on your source data, even though OLTP workload is going on, you will not see a degradation in transaction throughput or response time because of database and memory. So it's very efficient because in the background we're running these repopulation tasks for data that's changing, and it's really, if you think about it, database and memory is just CPU and memory access. We're not doing I/O. We're not having to serialize access to the column store because it's effectively read-only. And so this repopulation that goes on in the background is actually very efficient and allows you to be able to take advantage of OLTP workload and analytic reporting in the same environment, or what we would call real-time analytics or mixed workload. And so prior to this, you've had to maintain an I/O to keep indexes up to date, to access the data required I/O. And so usually people will move their analytical reporting workload off to either a data warehouse, maybe a decision support system, but typically aren't able to run the kind of analytic queries they'd like to run right on the source data with database and memory. That's possible to do. That's one of the really exciting things about, I think, about database and memory. So go check out the YouTube video. I've got a link to it here. Well, actually, when you get the slide, you can click on it and at the end. And so take a look at that. It's actually about 15 minutes. We go through quite a bit of setup and telling you how it's all working. And then we show you how it actually runs. And it's pretty interesting. So I mentioned the fact that you don't have to change SQL. So what does the optimizer know? How does that work? So at parse time, at hard parse time for your queries, the optimizer will take a look at your query, will determine the objects being accessed, we'll see if they're populated in the column store. If they are, it will go and take a look at that data in the column store, and at parse time will generate some statistical information that it can use to determine, based on cost, does it make sense to access that data from the column store or from the row store. This is how, in a mixed workload environment where we're running OLTP and analytics, you can actually have both, both queries run against either the row store or the column store based on cost. And so this is the real-time analytics part of database and memory. You don't have to say select from the row store or select from the column store. You say select from your objects, and the optimizer at parse time determines, based on cost, do I access that data from the column store or do I access that data from the row store, maybe through an index. And so it keeps track of this information, and we've exposed this in this all tab statistics view. In addition to that, it understands if you're in a RAC environment, it understands some of the options that are associated with database and memory in RAC, duplicate and distribute. And so it gets a pretty good picture of the cost of accessing that data from either the row store or the column store. It takes into account I/O cost and CPU cost. And remember what I kind of mentioned, that when you're running a database and memory query, it's CPU and memory access, because we're not Remember, the object's fully populated in the column store, so we're not having to generate any IO. So the question is, does the IO cost of going to that data in the row store outweigh the benefit of scanning that data in the column store? And so all of these factors are factored into the cost algorithm for the optimizer. So I just wanted to make you aware that it's actually very sophisticated how this is all done. You can actually even look at this if you want to generate an optimizer trace file. If you get that deep into the how Oracle works. In addition to that, in 12.1, we introduced something called optimizer, adaptive features. In 12.1, we had one method of doing it. In 12.2, we improved the mechanism for adaptive features. We broke it into two sections: adaptive plans, which actually worked pretty well out of the box even in 12.1, and then adaptive statistics, where we had some problems with 12.1. And so you can actually, what I've listed here is if you are still on 12.102, there are some patches that you can put on your system that will duplicate the 12.2 behavior. The reason this is important for database and memory customers is because obviously we're changing the plan. We're going to now access the data in the column store. We're going to do basically what's, and I'll show you with some execution plans, a table access in memory full, as opposed to how the query would have possibly run prior to having database and memory enabled. So the optimizer is going to be changing plans to take advantage of database and memory. And so these kind of issues become important. And so our recommendation, best practice for our tips and tricks for database and memory is if you are still running 12.102, you might want to consider these patches if you're having problems with adaptive features within the optimizer. In addition to that, we strongly recommend, because plans will change, putting or making use of plan stability, and that would be SQL baselines, if you will. The reason, again, is because you can expect prior to using database and memory, you'll have one set of plans. Enabling database and memory, plans are going to change, hopefully, because we want your application SQL that's doing analytics to take advantage of the column store. And so those plans are going to have to change in order to do that. And so it's always nice to be able to manage the plans so that you know what's changing and that it's changing for the better, not for the worse. One way to ensure that is with plan stability or SQL plan baselines. So one of the things, we have a white paper, the implementation and usage white paper, and our recommendation is to use SQL plan baselines to manage that transition to database and memory. And so that's why I've added this here, something to strongly recommend considering. And in addition to that, I guess I should mention, between the change of the plans that can occur when you enable database and memory and with the adaptive features, is that don't just run a query once. You need to run a query multiple times to get to what we would call a steady state, because the adaptive features of database 12c, 18c, and 19c within the optimizer the optimizer is learning as those queries are running. And so you need to run them more than once, because typically when people are testing, they just say, well, let's just see if it runs faster, as opposed to an actual running system that's running the same SQL statements hundreds or thousands of times. So take into account that, and this is the Oracle database, not necessarily database and memory, take into account that adaptive changes do occur, and the optimizer is learning what's going on with the access to the objects. And so that you need to think of running your queries more than once, running multiple times to get what I call to a steady state. And plan stability can help you with that, because then what it does is it keeps track of that, and then you can accept better plans as being faster for your queries, and you can control that execution, that plan execution, so you don't get any surprises, because every once in a while you'll get an outlier that might not run as well with database and memory enabled as it did prior. That does happen. And so you want to be prepared for that. This is one of those ways to handle those issues. Don't want to belabor the point, but I wanted to make sure I pointed it out. So how does database and memory scale out? We take advantage of RAC. I mentioned earlier that we use all of the features of Oracle Database. So RAC, I mentioned Active Data Guard. Um, uh, you can still run all of your RMAN, Golden Gate, all the features of Oracle Database that you're currently using will work with database and memory. We leverage RAC as our scale out solution for database and memory. So since we're allocating the column store, we're populating objects in that column store, you're limited by the amount of memory you have on a single database server. Now you can, each database server can only access, you can only put so much memory in a server. So how do you handle it if you've maxed it out? How do you make it even a larger column store? Well, you can add RAC, and that way each of your instances within a RAC cluster can have its own individual column store. The way we handle that is we distribute then the data across, and in this case, the 4 column stores. So now you can go from having, say you have 500 gigabytes on one column store, you could have 4 times 500 gigabytes or 2 terabytes of data total for your what we call logical column store, or your 4 column stores together. How do we access that data? We access that data through parallel query. So a query running on instance 1 can't access the data in instance 2, 3, or 4 unless we use parallel query. The reason for this is because IMCUs are not shipped across the interconnect. We don't do cache fusion like we do with the buffer cache. The reason is because those IMCUs, remember, an IMCU is made up of 1 or more 1 megabyte extents. We don't want to be shipping multi megabytes worth of data for each IMCU across the interconnect. So we use parallel query to access that data across each of the column stores. That introduces its own set of things to understand or to recognize. The big one, the big one is that you need to have your DOP, or your degree of parallelism, the number of parallel server processes, has to be at least as great as the number of instances involved in the query. What happens if that doesn't occur, or what happens if you run a serial query in this kind of an environment? Well, we get the data from the column store that we're running on, but we'll have to go to disk to get the rest of the data for the other 3 if we can't allocate parallel server processes across each of the nodes. So that's just the architecture of how database and memory works with RAC and parallel query. Hopefully that isn't too complicated. There's blog posts, and there's documentation, and there are some Ask Tom sessions about all of these things. So there's plenty of information. This is really just meant to be, oh, hey, remember that you can't run serial queries unless if you have data distributed across multiple column stores. In addition to that, when you're checking whether your objects are fully populated, if we're distributing the data across the column stores, then bytes not populated isn't going to reflect, or bytes not populated isn't going to reflect the actual scenario, because that object will be populated across, say, our 3, in this case 3 or 4 column stores. It's not going to be 0 because some of it'll be on one instance, the second instance, the third instance. So you have to take a little bit different look at the $IM segment view. I've included one of the queries that I use for that. The bottom line is you have to take into account all of the instances associated with the distribution of the data, not just a single instance. You have to get into the mode of RAC multi-instance mentality, which comes along with the territory. In addition to that, I did mention that on RAC, we do need additional shared pool space, that 10%. The reason is we're taking into account managing the data across the different column stores. And there is that note that I mentioned earlier, and I have it here as well. So I want to make sure you understand that, because Oracle customers tend to run pretty memory tight. There's usually not a lot of extra memory, and so you need to recognize that on RAC. Not only are you going to allocate additional memory for the column store, you're going to need to allocate additional memory in your shared pool as well. On engineered systems, we actually allow you to duplicate or mirror IMCUs. So you might ask if I have my data across 4 RAC nodes, if one of those nodes goes down, obviously I can't populate that data into that column store because the instance is gone. What happens? We have to access that data that was populated in that instance from disk. So it's going to be slower. On engineered systems, we support something we call duplicate. So we allow you to mirror IMCUs across multiple column stores. So this way, if one node were to go down, that data would be mirrored on another node, which would still have that data in the column store. So you can preserve performance, basically. So let me talk about a little bit about indexes. We're almost done, and we have our quiz, and I want to go ahead and answer some questions. But real quick, indexes. So Larry, I think when we first introduced database in memory, and sometimes people have the impression that you can drop all of your indexes because database in memory is doing table access in memory full. That's not really the case. You can drop your analytic reporting indexes because database in memory is not going to use those. But you still have to keep your OLTP type indexes, your primary key, foreign key constraints, or indexes that are enforcing those constraints. You may have lookup indexes that you need to look up just a small number of rows, but the analytic reporting indexes you can remove because you don't need them if database in memory is being used, because database in memory won't access those indexes. The reason that is a big deal is because indexes actually slow down OLTP, they slow down DML. So if you can eliminate a whole slew of analytic reporting indexes, typically you can gain considerable disk space, reduce undo and redo generation, and overhead of keeping those indexes up to date with CPU. So you can actually get some significant benefits, and we have a couple customers on our oracle.com page that talk about being able to justify database in memory because of that reduced workload. Important point. Actually, I'm going to slowly, I think, run out of time here, but I've got a few minutes. So let me just go through this because I think it's important. I'll be a little brief. All of this is documented in the implementation usage white paper, but what it's kind of important to determine, well, how do I know that I'm getting benefit from my queries running against the column store? And I strongly recommend that you use some time-based analysis technique. We recommend, from being Oracle, SQL Monitor Active Reports, because it not only reports the time spent by a query, but where the time was spent, and it takes into account database in memory. For instance, notice I have here, I'm not trying to be fancy, but I tried to highlight the fact that in this case, this query is running against the line order table, doing a table access in memory full, and notice that all of the activity down below there is 100% is on that bar. Well, that bar, if you hover over that bar, it'll actually tell you, it'll differentiate between CPU spent in memory and CPU spent doing something else. It'll be a different color, it'll be a gold color if it's not in memory CPU. And so that makes it very handy to be able to determine, one, did I access the data in memory, known as table access in memory full, and how much time did I spend doing that as opposed to maybe sorting or joins or whatever. So very useful technique to use SQL Monitor Active Reports. I have a brief on the blog that describes both within Enterprise Manager or standalone how to generate and use a SQL Monitor Active Report. And so I highly recommend using this method to determine both before and after, with and without database in memory, how much benefit you got from the column store or having that data populated in the column store. So database in memory is going to benefit scans, columnar scans, pushing predicates into those columnar scans, hash joins, and group by aggregations. That's what database in memory speeds up. Access of data within the database. And so things like sorting, transferring millions of rows back to your application tier, those things aren't going to get sped up by database in memory. Database in memory is focused on scanning lots of data, joining and aggregating it, and providing an analytic result set back to you, having done all of the work that it can within the scans of that data in the column store. So I'll very briefly touch on how that works, and then we should have time for some questions and answers. So using SQL Monitor Actor reports, a typical scan could perhaps use an index, scanning the line order table. And we see that we spent all that time accessing that data through an index. With database and memory enabled, we see we spent all that time and the same basic query as I showed you before, doing a table access in memory full. Notice that the plan is now changed. So we're doing, the SQL plan has changed to take advantage of database and memory. And by highlighting, we see that table access in memory full. Whoops, I thought I had, I guess I didn't have and from before, if you highlight over that activity bar, you'll say CPU in memory. Joins, a hash join. Hash joins can be turned into scan and filter operations with database and memory. Notice here, even though it's an in-memory scan of the 3 tables, our hash join is taking up all of our time, 63% of the time. Database and memory has the ability, using Bloom filters, to turn a hash join into a scan and filter operation. Notice now, almost all of our time is spent table access in memory full. I don't expect you to remember all of this. This is all fully documented, just giving you clues as to how you can leverage or understand that database and memory is benefiting you. Also notice that our total duration time is now much less than it was before as well. So it's faster in addition to leveraging database and memory, which is of course the point. And notice here, we will see Bloom filters, table join filter create on line 5, and on line 7, join filter use. So these are all clues that you're leveraging database and memory features to take that hash join and make it much faster than it runs without the ability to use that within database and memory. In addition to that, something you probably won't have seen before is with a group by. So traditionally, Oracle supports sort group bys and hash group bys. And notice the time spent in that operation. And this is actually a little larger queries. It's run for a total of 15 minutes here. And with database and memory and something we call vector group by enabled in memory aggregation, and there's an entire white paper dedicated to this, we can turn all of this activity that was going on before into basically a scan and filter operation of our line order table. And we've reduced the time from 15 minutes to 5 minutes. Notice here that we're now using something called a vector group by, line 30 there. So this is something you'll only see with database and memory. It falls under the feature of something we call in-memory aggregation. Like I said, there's an entire white paper that describes how this works. But effectively, what we're doing is we're not only doing the access of data in memory in the column store, we're doing the join, think of maybe a star query, we're doing the join in memory in the column store, and we're doing the actual aggregation, the group by aggregation in memory as well, in something we would call a report accumulator. So what this translates to is significantly better performance for large data queries where we're joining data, we're grouping by data, we're doing aggregations, think analytic queries, much faster than you can do without database and memory. So we made it. Back to the very end, I mentioned this several times on our blog. If you just go to the blogs.oracle.com in-memory, we have lots of posts about technical features and other things that are going on with database and memory. In addition to that, the URL I have here is our resources page. And on that resources page, I have the white papers listed. I have our YouTube videos listed, that YouTube video for the real world performance team that shows what's going on with real-time analytics. Lots of information, our hands-on lab information, all sorts of stuff on here. So that's what I consider our portal into all things database and memory, which is why I highlight it here. With that, I will, whoops, looks like I've run over a little bit, sorry, Sai. But let's go ahead and tackle what, I guess, the questions you might have had. And I think we have a live quiz too, I think, or something going on. So with that, I will stop.
Yeah, thanks, Andy. Awesome. It's okay. Yeah, we have taken a couple of minutes at the initial time. So we have received around 8 questions. Why don't you pick some of the questions from the Q&A panel?
Okay. Can people see this or?
Yeah, maybe you can just read out because
Yeah,
this
I
is also
will, but
live in the
okay.
YouTube. Yeah. Mhm.
So let's see. First question was, can I set the in-memory by pluggable database or only at the global database level? So I didn't actually mention that. We do, and I do in some of the other sessions. So obviously multi-tenant is going forward is the only option folks have. Database in-memory works with multi-tenant. The column store is allocated at the CDB level, and the in-memory underscore size parameter is available at the PDB level. So you can divide up the column store amongst PDBs. So the answer is you can set it at the PDB level within a multi-tenant or a CDB database. Hopefully that answers that. And then he's also thinking about the parameter. So the in-memory underscore size parameter exists not only at the CDB level, but can be allocated also at the PDB level. So you can essentially have subsets of the total column store for each PDB. Next question was, what is the retention period or age in memory? Hopefully I answered that question. There isn't one. So you alter a table to be enabled for in-memory. It's populated asynchronously in the background. It stays populated until you basically do an alter table no in memory or the instance goes down, because obviously it's in memory. But there's no aging out. It's not a cache. When does table store in memory? Well, when you do an alter table in memory. So you have to enable objects for in memory. Now, I should qualify that with saying that in 18C and in a future release, which has been delayed because of all of the things going on in the world today, we have something called automatic in memory. And so where we're headed is allowing the Oracle database to automatically populate objects in the column store. But for all intents and purposes, you have to say alter table, whatever the table name is, in memory to enable it for in memory. Hopefully that answers that question. Now I'm gonna get lost. The questions are coming through. So let's see. When does table store in memory? When you enable it. Is any setting required to segment in memory like a buffer pool and storage clauses? So I think what the question says is, do I have to worry about things like PCT free, PCT increase, maybe some of those old style storage pool allocations that we'd have to make for the row store, table space, extents? And the answer is no. All you do is alter table in memory. You can specify things like priority, compression, distribute, duplicate, which I kind of went over in the presentation, but there aren't any storage clauses you have to worry about. Active data guard. If we keep 1 year in memory on standby, standby goes down. So again, takeaway is this is the in-memory part for the column store. If the instance goes down, then we have to repopulate that data into memory again when the instance comes back up. This actually isn't any different than it is with the buffer cache, but with the buffer cache, it's typically just onesies, twosies with individual database blocks. So you don't see a large, although except for on the first time when you have to do a physical read, but you don't typically see that. With database in memory, since we're populating the entire object, then it takes more time because we're going to put the entire object into the column store. So even on active data guard, that's true. If the standby were to go down, one of the things that can be used on the primary or on a normal database in memory installation without active data guard is something called fast start, which we can checkpoint and keep track of the contents of the column store to make restarts a little bit faster. That's actually not available on standby on active data guard, but again, the takeaway here is that's the in-memory part of database in memory. And so again, if the database crashes, we'll have to repopulate at startup. Parallel query. So will in-memory queries be parallelized across servers if parallel force local parameter is set to true? The answer is no, because again, we're leveraging Oracle database and we're taking advantage of Oracle database features. So if in parallel query, you've said, I will only allow, so parallel force local says, my parallel server process can only run on the node or the instance that I'm invoking the query from. which means we can't then, because of that parameter, schedule parallel server processes across other instances or nodes, which means if you've distributed data across different instances, as I showed in the rack slides, then you wouldn't be able to access that data from the column store in those other nodes. So they are exclusive. Now, there is a feature where you can distribute by service. So you could limit your data to just an individual column store based on service, and I won't go into any other details. So there are options, but we'll honor, obviously, because we're just leveraging parallel query. So if you've changed the way parallel query works, database in-memory is constrained to operate within the architecture of Oracle Database. Hopefully that answers that question. Another question, and Sai, stop me if I run out of time here. In-memory benefits for spatial database. So spatial indexes, that's something that's coming in a new release of Oracle Database, where we're going to take advantage of having spatial indexes in the column store. So that's coming. It's not currently available, but we are moving in that direction. Again, we're trying to enlarge the options and the application usage of database in-memory as much as possible. So that is coming. What happens if the in-memory capacity is full? So if the column store fills up, that $V in-memory area I showed you, when that gets completely full and you can't populate any new objects, or existing objects, say, overflow, if you will, they grow, kind of mentioned this, then we'll have to access that data that has not populated into the column store from the row store. So your queries will run, but they won't be as fast because we'll have to go to the row store for data that's not fully populated in the column store. I should mention that it is possible to dynamically increase the size of the column store. It assumes you have enough memory in the SGA to accommodate that. You have to do an alter system command, set in memory underscore size, and you can make it larger. We can do that on the fly, so you might be able to accommodate overflow or data that's filled the column store. But that assumes, again, within the SGA of the running instance that you have room for that. That's available in 12.2 and above. So there is a little bit of a way around that, but your application won't fail. It just won't be able to access the data that no longer fits in the column store. It'll have to access it from the row store. Query performance if I run over a DB link. Well, if you run over a DB link, if the data is in the column store on the other node, then we could access that data from the other node, but we're going to have to bring it across the network. So that kind of defeats the purpose. So you're really going to want, if you want the fastest performance out of database in-memory, you're going to want those all those objects to be local. It'll still work. We'll still access data across the DB link, but obviously at the performance end of it, that would be like sending, thousands of rows or millions of rows off to your application tier as well. That's the time for over SQLnet is going to outweigh the benefits that you got from accessing that data in memory. Data keeps coming in for, yes. So, well, let's see. The question is, and data keeps coming in for in-memory tables. What I think that means is that as you're loading or changing data, we'll continue to add new data or repopulate change data to the column store, and that's true. Once you commit, then the changes will get reflected either in metadata initially, possibly, or in background repopulations of individual IMCUs. So the column store is always going to be changing, if you will, in flux based on what's going on in the row store, because the data always changes in the row store and we reflect it in the column store by populating in the background, keeping track in metadata, and always giving you a read consistent view, just like we do at the row store, of that data. And last one, how to determine which objects are ideal for in-memory. So the ideal objects, and the first way to do that is what I mentioned about the in-memory advisor. That tool is an excellent tool. The other way to think about it is what I tried to show is the 3 areas that benefit the database in-memory benefits: scanning and filtering data, joining data, and aggregating data. So if your queries are dominated by those 3 aspects, then database in-memory is going to benefit you. If instead your query is spending all of its time sorting data, then database in-memory isn't going to probably help a whole lot unless you can aggregate that data and reduce the need for sorting in the first place. I guess there's 2 more questions here. Well, now they just keep coming. I'm just going to keep answering until somebody stops me. So any TPC OLTP DSS benchmark done with in-memory feature? If yes, performance benefit for the workload. So I usually tell folks that I expect at least a 10x performance improvement for a query going from the row store to the column store. 10x is a pretty reasonable expectation. Are there any benchmarks? Oracle typically doesn't do benchmarks. The only benchmark I know of is one that was done based on SAP HANA, and that's out on our website. You can, I have a link in the resources page where we ran SAP's benchmark and had significantly better performance than their HANA database, and it was their benchmark. So other than that, I don't know of any other benchmarks. And to be honest, benchmarks are only worth the value of the benchmark against the data that's part of the benchmark. Your mileage is always going to vary based on your data because nobody's the same. So my recommendation would be to try it. That's really the simple, because as I've hopefully shown, literally all you're doing is populating your objects and running your application. There's nothing else you have to do other than keeping track of how much faster it is. If data is found in the row store due to staleness in memory, due to DML, how is the performance affected? That's actually an excellent question, and one of the things we were trying to show with that real-world performance demo on real-time analytics. Your performance is not going to be affected all that much. The bottom line is that we're still getting that data typically from the buffer cache in memory in the buffer cache, as opposed to having to go to disk. And typically, unless you're changing all of the data in a table, which means you probably ought to take it out of in-memory, change it all the data, and then populate it again, because nothing's free. We still have to keep everything in sync. You're not going to notice the difference. And most of our customers don't notice the difference. And that's an area where, or especially the DBA types and the technical folks get concerned, compression and DML. And the reality is that in both cases, it's typically not noticeable. Is repopulation automatic or manual? It's automatic, but you can specify through a DMUS in-memory admin to repopulate through PL SQL or to an API. But repopulation is all automatic. Everything with database in memory is basically automatic in the sense that other than altering the table to be enabled for in-memory, after that, everything takes care of itself. And then the last one is there any query available to list out what indexes are required to rebuild? Well, that doesn't have anything to do with database in memory. And to be honest, there's almost never a requirement to actually rebuild an index. And if you really wanted to find out what indexes might require a rebuild, there are other, maybe the Mike Dietrich's upgrade page or some third-party features. But basically, the only real reason to ever rebuild an index would be if you had very sparse, the index was very sparse for some reason, or you had an empty front, but that's beyond the scope of what we're talking about here. So I'm going to leave that alone at this point. All right, I think that's all the questions.
Awesome, Andy, and thanks once again answering all the questions, and thanks for your support to present in AIoT forum. Hopefully we will schedule your next session very soon. So one of our AIoT tradition is to take a selfie with speakers and thank them by tweeting. I'll project your banner now. People, if you guys are really take a selfie with speaker, please take it with your monitors and use hashtag AIoT virtual selfie or AIoT webinar and tag to Andy. Andy's Twitter ID is really funny, the in-memory guy.
Yep,
So use that.
guy.
Yeah, in-memory guy. So use that, and thanks to speaker. So now time for us to go for a real exam now. Okay, so you need to go to menti.com and use code 2818 and 78. So we have already 20 players actually. So let's wait for one more minute. People join. So one of the important things, please provide your full name. Okay, then only you're eligible for this, gift coupon. If you just say A, B, C, D, so we can't identify that particle. So make sure that you provide a full name. Okay, so I'll just wait for one more minute. Yeah, join. It's really good to understand, basically check your knowledge. Okay, I'm going to start now. So we have around 32 players waiting for the game. Start quiz. So the important thing is answer the first. Okay, I'm not going to talk now, so read question and answer. Excellent. So we have 18 answers, correct answers. Going to the next question. Oh, sorry. So let's look at the leaderboard. Wow, we have Vishwanath MWV. So let's see, Arun is also going up. Okay, let's see next one. Okay, something is wrong. Give me a minute. Actually, it started with the last question once again. Sorry for that. So you can start one more time. Excellent. So we have 11 correct answers. Going to the next question. So sorry, before that, we have a leaderboard. So we have Ajay leading the board, and he's the fastest to answer the next question. Wow, 23 right answers. Let's see the leaderboard. Ajay is still leading and Amit is coming. 25 right answers. Let's see the reel. Ajay is still leading. I think this is the last question. I think we already answered. Congratulations, Ajay is this week's webinar's winner. Ajay, I think again, it's important. Maybe you can put your full name in the YouTube channel. That's very difficult to find. Ajay, we'll find out. But if you just provide your full name in the YouTube channel, that will be great. Okay, guys, so let's see who's actually coming next week. So we have next week from one of the key topics, system changes and go live. Avoid sleepless nights using Oracle Real Application Testing, 29th April at 2 p.m. IST. So for registration details, please watch out our Facebook channel, and we will release all the registration links today itself. Thank you. And also, we will send you the speaker evaluation form after this. All the registered people, please fill this form. And after that, you can basically able to access the presentation soft copy. Okay. Thanks a lot. Thanks, Andy, once again for your support, and we'll see you soon.
Yes, you're welcome. Thanks, everybody.
Thanks. Bye.